can move to the next speaker. So Zibi, maybe you do the introduction. Check.
Yes, thank you. The next talk will be an online talk by Conor Nixon about recent observations of Titan with Ground and Space Observatories. And Conor, I can run your slides from here. Hopefully you're seeing them on the Zoom.
Okay, good morning, everyone. Can you hear me?
Yes. Okay,
excellent. I want to thank Athena and the rest of the organizers of this workshop for inviting me. I'm very sad, as I'm sure you can imagine, not to be in Paris in person and eating pain chocolat with you and drinking good coffee. But we'll try to make up for it with some science. The talk that I was invited to give was to cover some of the ground-based observations of Titan, particularly post-Cassini, but I'm going to stretch back a little bit further into the into the kind of the last decade, but mostly in the post-Cassini era, and kind of talk about what we can do now that we don't have this wonderful spacecraft, of course, is gone, what we can do between now and Dragonfly. Okay, next slide. So I was going to cover the ALMA, but Martin's given a really great summary of that already. Thank you, Martin, for that very comprehensive talk. I'm going to talk about some other subjects which are close to my heart, with the caveat that I'm not going to be able to cover all of the ground-based and space-based observations that are currently underway, because there's a lot, and many people in Madonna, in fact, are involved in using many different observatories. So I'm just going to cover the ones that I have a personal knowledge of from my own work. So next slide, let's begin with some RTF work. Okay, next slide. So I was actually out at this observatory last week when you were all, many of you were in Helsinki, I think, trying to do some more high resolution spectroscopy using this TEXES instrument. This is the instrument that was built by John Lacey, University of Texas, about 25 years ago, and was able to do very, very high resolution shell spectroscopy over narrow wavelength ranges in the infrared. And some of you are probably familiar with this detection we made about 5 or 6 years ago. This was data that was taken in 2017 around the end of the Cassini mission, actually kind of in the last year of Cassini. It was published in 2019. And it shows this nice detection of propydiene, which is like a double bond isomer of the propyne molecule, the C3H4 that Athena mentioned was discovered back by Voyager Iris in the McGuire paper. So this was a nice example of isomer. This was the second isomer discovered on Titan after the HNC molecule discovered by Raphael. So we were able to get a second isomer. You can see here, just to kind of zoom in on that little line in the lower right corner. Next slide, please. And together with the C3H2 that Martin has mentioned, this has enabled us to kind of fill out part of this family tree of 3-carbon hydrocarbons. Of course, we were able to detect propene C3H6 using Sears from Cassini back in 2013. And probably at this point, we're looking at the major undetected isomer of interest being this cyclopropane C3H6, which we're still in the process of trying to see if we can find that one. It's predicted to be at about 100 times less abundance than the propene. And there's maybe a few other exotic isotopes of C3H2 lurking in there as well. But you can see that we've been able to kind of fill out some of this diagram with a couple of new detections since the end of Cassini in 2017. Next slide, please. And I wanted to show this. This is unpublished work, actually done by Nick Lombardo, who again did the previous work with the propydiene in another wavelength range close by. He was able to show that there's a line here, which you can see kind of near the center, lurking between these 3 very strong lines of ethylene, and using some fairly decent integrations, we're able to see this bump here. And he has now shown that this can be modeled with HNC. So this would be the first infrared detection of HNC, which of course, as Martin has shown, is detected pretty easily now by ALMA, and before that by other observatories, including Herschel. But we're trying to get this written up for publication And this will give us a point, another data point on the HNC. Next slide, please. So you can see here, this measurement, we have the, in pale blue here, we have these kind of profiles that are derived from the ALMA work. And then this kind of red dot brings in a new measurement in the very lower part of the atmosphere, around 100 kilometers. And you can see that this is kind of a little bit of an increase compared to what some of the photochemical models would show, in particular models that are not including galactic cosmic rays. They would indicate an abundance somewhere down around 10 to the minus 12 in the lower part of the atmosphere. But in fact, we're seeing something around 10 minus 9, which is pretty high. So that indicates that maybe these GCRs are quite active here, and that this GCR profile from Vuitton et al. Is something that we need to consider. Still not getting quite a good match up there. So there's more work to be done. Anyway, this paper's now in preparation, so kudos to Nick for working on this. Next slide, please. Let's move on to Sophia. And this work actually was presented last week in Helsinki, so I'll go over it pretty quickly, but I just want to include it for completeness. These were EXIS observations that I proposed back in 2021 using the sister instrument of TEXIS that was on Sophia, which unfortunately was grounded in 2022, which is a great loss to science. But at the time we were searching for a couple of heavy linear molecules, including triacetylene, C6H2, and also C4N2, that's a dicyanoacetylene molecule. And these black boxes here show where the molecule would be if we detected it here. You can also see there's some gaps between the orders due to the design of the instrument at long wavelengths. And then there's some other pretty prominent lines of known molecules, including the C3H4 and the C4H2, which were the same bands detected all the way back with Voyager Iris and then redetected with Cassini Sears. We can see these lines pretty nicely resolved now, but these are all lines of molecules that were already known. Next slide, please. So again, showcasing some work from Zach's paper, which is hopefully about to be submitted. On this slide, we see the retrieval of the C4H2 and the C3H4. The main things I'll point out is that the C3H4 in the lower right corner there is matching pretty well to the photochemical profile from Vuitton 2019. In contrast to the C4H2 in the upper right there, which you see the retrieve profile is about an order of magnitude lower than the Vuitton et al. Profile, and we believe this is actually going to give us some impetus to change the chemistry a little bit in the model. So on the next slide, I think we talk about that. So the main route for diacetylene loss, which is proposed, is a combination with hydrogen, which gets rid of the diacetylene by transitioning to C4H3 and then to other species. What we're seeing is that because this diacetylene seems to be a bit lower than predicted in the model, that indicates that there's more hydrogen around, and that a process which is in Veronique's model for heterogeneous loss of atomic hydrogen onto haze particles may be overestimated. So basically, the hydrogen loss is overestimated. There's probably, we think, maybe more hydrogen around, and that's causing more of the diacetylene to be around. In contrast, here on the right, you can see that we're seeing quite a bit less of the triacetylene than expected. So there's some previous upper limits shown there with the triangular point and the diamond point, and then our new data point in the square. Okay, next slide, please. And then for the C4N2, again, we've lowered the upper limit here with our point here as the gray shaded square. We're still not really constraining anything close to what the C4N2 is expected to be from photochemical models, which is very, very, very low abundance. And of course, there's a well-known mystery because there's a C4N2 ice feature detected by Sears and even Voyager. And Carey and others have postulated that this is created by solid-state chemistry through reaction of HCN and HC3N. So we're definitely pushing down the upper limits on the gas profile there, and that's further limiting the indication that this would be this ice feature be directly formed from the gas phase. Next slide, please. Moving on to JWST and Keck, I'll go through this pretty quickly because I think some of you have seen it before, but the paper just came out this year, May 2025, and Zibby and others in the room were co-authors on this work. We used 3 instruments on JWST. Maybe let's go to the next slide. This was a project using 12.5 hours that we had from Heidi Hamel's GTO project, spread over 2022, 2023. So we looked at Titan twice on the leading and trailing hemispheres. Next slide. And you can see here the spatial resolution. So one of the things that Benoit actually pointed out in his nice talk earlier is that spatial resolution is a very significant problem still for Titan's surface. And with JWST, we're not going to really push any boundaries in terms of spatial resolution here. So what I've shown here with the kind of hatched indication is the pixel size on JWST for NearCam, NearSpec at the top, and the near infrared, and then for MIRI in the bottom. And of course, you need bigger pixels to sample the bigger PSF as you get out and the longer wavelengths. The background image, of course, is the VIMS image, not a JWST image, just to show for comparison what sort of resolution we're getting. So we're not pushing boundaries there, but I think with MIRI, at the shorter part of MIRI, we are able to get some hemispheric resolution, which should be coming out in future papers. Next slide, please. So Benoit also showed this figure here. This was our very first image of Titan with JWST on November 4th, 2022. In fact, my son's birthday, so that was a nice birthday surprise. And then a couple days later, we got companion imaging with Keck when we kind of called up our friends there and asked them if they could very quickly go and confirm what we were seeing. And we saw these clouds in the northern hemisphere, which is apparently kind of in our rain belt. Next slide, please. And then over the next year and a bit, we were able to fill this picture out a little bit more. There's actually only 2 of these vertical columns here from JWST, if you look closely, and everything else is from Keck, where of course we can get a higher time cadence. We don't have to, fight quite as much for the time. In fact, there's a nice program which is underway by started by Imke de Pater, Catherine de Clear, and others for twilight observations. And we're able to use that to get some of these time series here. You see some clouds coming and going, particularly in some of the filters that are sensitive to the troposphere. And then we were able to see one cloud kind of breaking through into the stratosphere, which you see just in the last column there. And I know I don't have a lot of time, so please go and read the paper if you'd like more details on that. And a nod to Sebastian Rodriguez, who made this nice figure. I hope he's in the audience. Okay, next slide, please. And Juan Laura, who I believe is there, made this figure just showing comparison between the clouds and the model predictions, showing that we're pretty much in line with what we expect for this time of year, seeing clouds in the north at this kind of ICTZ, which is moved close to the North Pole this time of year. Next slide, please. There's kind of a cartoon here. This is also found in the paper, which shows that because of Titan's mostly kind of single cell pole-to-pole circulation with very small polar cells, we're seeing the clouds kind of where we'd expect them to be, around 60 north at this time of year. Okay, next slide, please. And then the near spec, there's a figure here, was put together by Mile from our paper, showing the different detections, and we're kind of digging into some of this work. I'm not going to go into detail of all the modeling that's been done by Bruno, Emmanuel, and Manuel and others, which is all in the paper, which shows some very nice detections of near-infrared bands, which were not clearly seen by VIMS. So the big advantage here is the spectral resolution. We don't have high spatial resolution, but we do have high spectral resolution compared to VIMS by about a factor 20. And this has enabled us to get some nice fluorescent emissions that were not clearly seen before, and that's giving us indications of vertical abundance profiles of some of these molecules. Next slide.
5 minutes.
Okay, thanks. Thanks, Zubi. And then the MIRI spectrum here, this was a plot that was made by Nick Teenby, showing the MIRI spectrum here as calibrated by Brandon, Oliver King, Mike Roman, others. And the main thing I want to point out here is, first of all, the spectral resolution is the same as Cassini-Sears. So we have a half-wave number resolution. It looks a little bit cleaner because the noise is very, very, very low with the very cold detectors that we have on JWST. But the spectral resolution is actually the same, but we see these bands pretty clearly. So the big advantage with MIRI over Sears is that there's a few parts of the spectrum we're very close to the noise level. We've got low flux levels, and it was quite noisy with Cassini-Sears. But using MIRI, we're actually able to dig down further and see some very weak features. And you can see, perhaps if you squint a little bit, there's a CH3 indicated in the lower, or sort of on the right side of the diagram here. And if we go to the next slide, I think there's a blow up of that. So in the center here, you can see the spectrum of CH3 compared to a model prediction. And this was the first detection of a radical, or at least the first remote sensing detection of a radical species on Titan. And of course, CH3 is not unexpected on Titan. In fact, we know that it had to be there due to the breakup of methane. But being able to measure it directly is actually is quite nice, and it's kind of giving us a bit of a missing link in the chemical pattern. So there's quite a bit to dig into here. Again, I'll let you go and read the paper. I'll mention that there's a follow-up paper on this being worked on by Nick Teenby. I think he gave a talk on this actually last week at Helsinki as well. And we've done a little bit of a better job cleaning up this modeling. So that'll be in a future paper. Next slide, please. And then I want to mention briefly some occultations that were done. Next slide. And this is some very nice work. It was kind of a joint campaign by quite a lot of people. We proposed to look at this star going behind Titan back in September 2022. And very conveniently, the shadow of Titan went right over Mauna Kea, which was like really just spectacularly convenient for us. So we were able to use Keck, Gemini North, IRTF, and a Fox telescope. And the data in particular from Keck, being the largest aperture telescope, was very nice. And that's now being modeled, and it's a paper which is accepted. I think it's not quite published yet, but it's in press by Teresa Marlin as part of her PhD work with Catherine DeClear at Caltech. Let's take a quick look at those. Next slide. This animation here shows just the raw data that we acquired. This is using adaptive optics, using the NIRC 2 camera on Keck, and you can see the star going behind Titan. And if you were very careful, you might be able to see a sort of magnified image of the star going around, or refracted image, sorry, going around the edge of Titan. And on the next slide, we'll see what happens when you take Titan out of the picture. Now you can actually see that image of the star kind of wrapping around the edges as it goes through there. What does this tell us scientifically, or is this just purely curiosity? Well, in fact, the shape of the atmosphere determines the refraction profile, right? So if we go through some pretty complex math, you can actually show that you can get the wind speed. So the wind deforms the shape of the atmosphere. The shape of the atmosphere creates the shape of the lens, which does the lensing. And then by doing some complex modeling and getting the exact path of the star, running a whole bunch of forward models, you can see which one best matches the data. And here on the left, we show what we think is the wind profile that was going on. I'd encourage you all to go and read Teresa's very nice paper, which goes into all of this in exquisite depth and should be online pretty soon. Next slide. I think we're just about at the end.
2 minutes.
Yep. Okay, perfect. Next slide. So I wanted to mention we're not done with JWST. In fact, at the same time as we were proposing these observations using some GTO time from Heidi Hamel back in 2022, 2023, Jonathan Lunin actually also had some time available to look at Titan as well. And after deciding what to do about that, we decided to postpone those observations a little bit so that we would get a different time period. And those observations are now being executed this year, in fact, which is really nice. We did get some NIRCam at the end of last year, but the key NIRSpec and MIRI observations are being done this year. We had a couple of hemispheres done in July, and we're looking at the rest being done in the next couple of months. So this is actively ongoing work. Very exciting. This is giving us a look at Titan right after equinox, which occurred just back in May of this year. So this data is now being worked on actively by Jonathan, his team, in particular, I believe Maria Comarca from Caltech has now transitioned to doing a postdoc to look at this data. So so very exciting. We're hoping to get more results and more JWST results for Titan once this data is analyzed. Next slide, please. And maybe if we're lucky, we could catch something like this that I think was in one of Zibby's publications back in just after the last equinox, and this shows this really big storm kind of sweeping across Titan, which seemed to darken the surface with methane rainfall, at least temporarily. And we were hoping to catch something like this again. Unfortunately, many of our observations that we proposed to try to catch this in action with Keck have not been accepted. So we're going to try to see what we can do using our Twilight campaign and hopefully catch something like this in action again. Next slide, please. And then looking towards the future, there's these large observatories being built. Right now we're working with Keck being a fantastic. You've seen some of the resolution we get with that at 10 meters. Once we get to the kind of 25 meter class with GMT, and especially the nearly 40 meter class with ELT, which are coming online in just a few years, then this should be really spectacular for looking at Titan clouds. Maybe we'll actually be able to clean up some of those parts of Titan surface that Benoit was talking about using this fantastic resolution. We're going to be getting, close to 100 pixels sort of scale on Titan. So it'll be really, really spectacular and just a few short years away. So with that, let's see what we have for next slide. Big shout out to all the people who are involved in the JWST and Keck campaign. And then on the next slide, all the other collaborators as well. I probably didn't catch all of them, but as many as I could think of. And yeah, that's the end of my talk. Thank you.
Thank you, Conor, and thanks for being up so early in the morning there. We're running a little behind. If there's a quick burning question, we can take that as we're transitioning to the next talk.